We're going to start with slopes of lines with this lesson, this intro to derivatives. You guys have been talking about slopes of lines since algebra. Okay, we know slopes of lines is like the pitch of a line. We say it's the change in the y values between 2 points divided by the change in the x's. You use the formula y2 minus y1 over x2 minus x1. Okay. If we're talking about a line that is going up from left to right, we say this slope is positive. If we have a line that is going down from left to right, we say that slope is negative. And if we have a horizontal line, we say that slope is 0. A vertical line, we say that slope is undefined. Okay, not new. Well, let's talk about average rate of change. Instead of talking about maybe a line and y's and x's, we'll talk about functions. The average rate of change of a function is the change in the function values over the change in your inputs. Well, if we're talking about a boundary, say the average rate of change of the function from a to b, well, then we'll be talking about the change in these function values f of b minus f of a divided by the change in the x's, which is b minus a. What does that look like? What does that look like? Slope of the line. An average rate of change of the function is the same as the slope of the line that is connecting 2 points on the function. If I want you to find, also, before we get into some examples, if I find the average, let's think about physics. We're going to be dealing a lot with physics, and I'm just going to use physics in a couple of our examples to introduce things. But then moving forward, we're going to be using physics a lot. And in physics, we'll talk about position versus velocity and versus acceleration. We use x of t for position. Now, what does position mean? Position is not a distance. It's not how far you've traveled. It is just where you are at a specific moment in time. If I have a position of -2, I'm just standing on the, the line with the number -2 on it, the number line. That's what I was thinking of. If I then go to position 4 over 2 seconds, I will move a total of 6 units up to position 4 over a total of 2 seconds. I can find the average rate of change of position. Position is in meters. You're in a specific meter. Okay? If I find the average rate of change of position, I will be finding the average velocity. So if I have position at -2 at time 1, and then I go to a position of 4 at time 3, the average rate of change of that would be 4 minus -2 over 3 minus 1. This would be 6 over 2, or 3. This is time. This is meters. This would be meters per second. Okay? So the average rate of change of position is an average velocity. Okay, that should not be super unfamiliar to you. We will talk about it a lot in this class. So let's take some position functions, and these could be just f of x's, and find average velocities. Or I could just turn these into functions, f of x's, and say to find the average rate of change of the function. Okay. Now visually, 2x squared minus 8x, 2x, x minus 4, would look something like this. I would be looking at finding the slope between these 2 points. At 1 and at 4, this line here, the slope is the average rate of change. Okay, so it's the change in my function values over the change in my inputs. So all I have to do to find this average rate of change, or to find the average velocity, is to find the 2 points. I need to find my function value at 1. 2 minus 8 is negative 6. And I need to find the function value at 4. 16 times 2 is 32. Minus 8 times 4 is 32. That's 0. Okay. Giving me my 2 points, I have the point 1, negative 6, and 4, 0. So I should actually be like over here. That slope would be the average rate of change in this situation. And then all I need to do is find the slope between those 2 points. Negative 6 minus 0 over 1 minus 4. Make sure we keep things in order. This going first means the 1 is going to go first. 0 going first means the 4 is going to go first. We have negative 6 over negative 3, which is 2. We could say 2 y units per x unit. If you want to think about functions, x's and y's. If we're talking about position, where this is meters and this is time, this would be 2 meters per second. This is the meter that I'm located at. So this would be actually a displacement that I found. This is the time that has elapsed, 3 seconds. That many meters displaced over that many seconds would be the average velocity. So either meters per second, if you're talking about x over t, or y's per x. Does this make sense so far? Average rate of change is the slope of the 2 points on the function that we can connect. So if I wanted to find the average rate of change of sine between 2 points, or if I want to find, some object has a position that is designated by this function sine, so the object is going to be going, forwards, then backwards, and forwards and backwards, and forwards and backwards. We can find the average rate of change between 0 and pi over 2. Be the slope connecting those 2 points. So I would just need the 2 function values. I'll use x of t here. So x of 0, sine of 0 is 0. And then x of pi over 2, sine of pi over 2 is 1. Okay, giving me this 1 minus 0 is the change in my my position. If this is in meters, this is in meters, and this is seconds. And 1 minus 0, I'd have pi over 2 minus 0 as well, giving me 1 over pi over 2, or 2 over pi. Okay, so on average, if I started at position 0 at time 0, and I traveled to position 1 at time pi over 2, I've averaged 2 over pi meters per second, my velocity. Okay? I could give you a table and ask you for the average rate of change, giving you specific values. Okay? So here, find the average rate of change of the object between 10 seconds and 25 seconds. What does your answer mean? Well, since this is position in meters, and this is time in seconds, if I'm going from here to here, all I need to do is just find the average rate of change, which is the slope of the line that connects the 2 points. Just average rate of change of my position or my average velocity from 10 to 25 seconds. Okay. Well, what if instead of finding the average velocity from 10 to 25 seconds, you can think of it as a speedometer, you know. I found that on average, my speedometer has read 19/15 meters per second between the 10th second and the 25th second. That's how fast I've been traveling on average. But what if I wanted to know exactly how fast I was moving, let's say at the 15th second? My position is 20, okay? It means at the 15th second, I'm looking at being at the position of 20 meters. What could I do? What do I need? So, you know, we think of velocity being our distance divided by time. Well, we're going to find distance by subtracting our position. Okay, so I took 25 and subtracted 6. I'd say my distance traveled between these 2 meters were 19. So that's how I found distance. I subtract the positions. 25 minus 6, 19. I've traveled 19 meters in 15 seconds. There you go. Okay? But that's just telling me on average how fast I traveled over those 15 seconds. I want to know exactly how fast I'm traveling at the 15th second. So all of a sudden, I take a cool selfie of my speedometer, which I'm sure is done when you guys are speeding. Take a quick little snapshot, and boom, at that moment, at the 15th second of me drag racing, I take a picture, and it shows me a speed, okay? How can I find that speed if all I'm given is my position? What do you think, Mr. Quigley? So you're saying position here is not going to do me any good. You're saying the position, the 20th meter, maybe isn't helping me. Maybe I should go a little bit to the left and to the right of this 15th second. Yeah. Well, that's a decent idea, Mr. Quigley. You're saying this isn't going to help me here. This is not enough information. It's almost like I need the 14.999 seconds and the position that I am there. Maybe I'm at 19.8. Maybe I need the 15.0001 second. And maybe if I find the average rate of change between those 2 positions, that is going to be such a small period of time that it's essentially going to give me a very, very accurate estimation of how fast I'm moving at this moment, right? That's a good idea. Well, to do that, we need more information. Well, here is more information. A graph gives you more information. Okay, these are all of my positions for all of these times. Siri keeps just getting hit up. Okay? And the question is, what is my speed at this moment? Now, again, this is a position graph, so this is just where I'm located. Now, what I could do is I could take, and this is what I found, my position at the 10th second and my position at the, say, 20th second, and connect those two. And what I would have found is the average rate of change over that time, the average velocity. Well, what Mr. Quigley is saying is that's not going to be close enough to my specific moment that I'm looking for. I'm looking for the exact speed at the 15th second when my position is right here at 25. Well, don't look this far away then. Why don't we look maybe at my position here and here? And you know what? Let's get even closer. Why don't we look at my position here and here? And let's find the average rate of change between those two. Well, if I connect those 2 points, we're talking about a really, really tiny line, right? We'll go ahead and extend it. What does the line look like? It looks like this. What would give me the best approximation? How close would my 2 points be? Like half a second away, 0.1 seconds away. I'm looking for an I word. Yeah, infinitely close together. If I took two positions where time was almost on top of each other, if I took my position at the 14.99th repeated second, and then my position at the 15.0000 many zeros first second, well, I have two distinct points. I can find the average rate of change of those two distinct points. However, they're so close together that it doesn't represent an average rate of change anymore. It represents an instantaneous rate of change, or an exact speed, an exact velocity. So all of a sudden, this is exact velocity. What do? I took 2 points that gave me average velocity, and I brought them infinitely close together around a specific location to then be able to see exactly how fast I'm moving. Does this make sense? This is the basics of what a derivative is. Derivatives you've probably heard of before. We talk about derivatives a lot in this class. And it's very simple. A secant line is just a line connecting 2 points on a curve. Let's talk about a curve. If I connect this point and this point, we have created a secant line. Now, the slope of this secant line, we say, is the average rate of change of the function. Now, what you just saw right there, we could describe as being a tangent line. Tangent line is a line that is just touching our function at a specific point. Let's take right here. I would draw a line that just touched the function at that point. Two points, average rate of change. Take those 2 points, put them infinitely close together, and we can extend those 2 points and create a tangent line. Still created by putting 2 points really, really close together. The tangent line, now the slope of that would be the instantaneous rate of change of the function at this location. We'll use IROC instead of AROC. Average rate of change of the function is the slope of the secant line. It's over the interval. A slope of a tangent line ends up being the exact rate of change, or what we say is the instantaneous rate of change. Okay? A derivative is a fancy math word for a slope of a tangent line. Or instantaneous rate of change of a function. Okay? By taking 2 points and making them infinitely close together, instead of talking about an average rate of change, we have an instantaneous rate of change. Instead of having a secant line, we have a tangent line. Let's go ahead and figure out how we can find this tangent line, some equation for this instantaneous rate of change. Okay? So we're going to start with a secant line and just some random function. This is a random function. It can be any function. And we're going to talk about 2 random points on my function. Okay, we're going to call this point right here, this is the point where we're going to find the tangent line, how we're going to have some sort of equation for it. We'll call this point x, which means this is going to be f of x. Then we will add some distance, we'll call it plus an h, to give me x plus an h, which means this function value up here, there we go, this would be f of x plus h. All right, well, let's start by writing the equation of the slope of that secant line. Okay, well, it's the change of my y values, which I would say is f of x plus h minus that f of x value divided by my x plus h minus my x. Okay, this is the slope of that secant. Are you with me so far? Do you understand where this comes from? It's just this point here, which we're designated as being just an x value plus an h distance. This will be that function value, f of x plus h. This is just f of x, okay? y2 minus y1, x2 minus x1. Well, I can actually simplify this and make it look a little nicer. What can I do here? Anybody see what I can simplify? Yeah, we have x plus h minus h, right? The x's will cancel each other out. So this is actually easier to write up. This is just the slope of this secant line is f of x plus h minus f of x all over h. Okay. Well, let's create a tangent line. I have 2 points. What do I need to do with those 2 points to have a line such that when I kind of connect and extend those 2 points, it looks like a tangent line? What do I do, Mr. Johnson? I'm starting with 2 points. What should I do with those 2 points? So that I just kind of move my line, and my line changes from a secant line to a tangent line. So you're thinking about going like right here? Well, let's kind of draw our tangent line right here over x. What do you think, Ms. Offord?
Bring them closer to the h values?
Yeah, we'll bring the 2 points closer together, right? So I could take this point and start moving it closer and closer and closer, right? What happens to my line? Well, my line, if I can grab it, there you go. My line starts moving this way, right? And here. Okay? We have still a secant line, right? Well, if I continue to take this point and move it closer and closer and closer together, I still can create a line. I can still calculate the slope. However, what's happening to the line? It's getting kind of shallower and shallower in this situation. And before you know it, if I take this point and put it almost right on top of this other point, I would still be able to calculate a slope. Now, why can't I put it right on top of this point here at x? Why can't I just make it 1 point? What do you think? And what happens to the average rate of change if we're just talking about 1 point and itself? That's exactly right. If I say had this point, and let's just use numbers for comparison. If I put both points at 2, 3, I would have 3 minus 3 over 2 minus 2 as my slope. What is that? It does not exist. It's undefined. So I can't talk about putting things on top of each other. This is where the whole process of a limit comes into play. This is why I taught you guys limits before we got straight into derivatives. It's because we need to take 2 points and put them infinitely close together. And we'll be able to connect and extend. And what does that create? A tangent line. Because the points are infinitely close together, it's like they're only at one location. They aren't at the same location, but they are essentially at the same location. But we can connect them and we can extend them. Now, what happened in my formula to go from 2 points here to just 2 points infinitely close together? What changed? I have x here where a point stayed. I added a distance. I got to x plus h. The points started getting closer and closer together. So this y value started to get lower and lower and lower. Because what was changing? H was changing. What was happening to h? It was decreasing. It was getting smaller and smaller. how small was it getting? Infinitely small is approaching what value? 0. Guess what I can do? Take the limit as h approaches 0 of the formula that I had for the slope of a secant line, and all of a sudden, this is the formula for the slope of a tangent line. There's an alternate way that I could have created this formula. I could have used 2 points, x and a. But if I did those 2 points, it would have looked like this. A would have been here. X would have been here. This would have been f of a. And this would have been f of x up here, those 2 points. We'd have f of x minus f of a all over x minus a, right? Does that make sense? That's the formula for the slope between those 2 points. What is happening as those 2 points get really, really, really close together? We would say that x would be getting really, really close to a. We could also say this is the formula for the slope of the tangent. A being the location where you're finding the slope of the tangent. Okay? Now, this is called a derivative. A derivative is a slope of a tangent. We have notation for derivatives that we will use, and that right there is the definition of a derivative. Definition of derivative is the slope of a tangent used by taking 2 points and putting them infinitely close together. Definition of a derivative, the instantaneous rate of change of a function, or it's a slope of a tangent created by finding the slope of 2 points infinitely close together. We say differentiation is the process of finding a derivative. We say differentiable, a function is differentiable if the derivative exists. Okay? Notation for derivatives. We will use f and a little tick mark we will call prime. At some value. This is the slope of the tangent of f at c is equal to something. This is short for just writing this. The limit as h approaches 0 of f of c plus h minus f of c over h. These mean the exact same thing. I could have also done the limits as x approaches c of f of x minus f of c all over x minus c. All three of these are the same. F prime is the same as that, It's all, what is the slope of the tangent of the function at this location, which is this location in this formula. All the same. Okay? Now, we'll come back to that. We can compare values for average rate of changes and instantaneous rate of changes. Okay? For right now, all you're concerned with is the slope positive, negative, or 0. We're not going to get into specific values. It's just going to be kind of eyeballing things and looking at slopes. Okay? So here is a function, f of x. We have 3 points A, B, and C. I could ask you, what is this? Positive, negative, or 0? Well, you have the value A. That's where x is. What this is the formula for the slope of a tangent of the function at A. What you do is you come over to your function and you think about creating a tangent line right at A. You can do better than that. How is it created? Well, it is created by using 2 points infinitely close together, but it's essentially just at one location, right? Because they're so close that they're pretty much on top of each other. What is the slope of that line, Mr. Rauschen? Positive, negative, or 0?
Negative.
It's negative. Boom. This is less than 0. If I gave you this formula, could you figure out if it's positive, negative, or 0? F of c minus f of b over c minus b. This is the average rate of change. This is the instantaneous rate of change. This is the slope of tangent. This is the average rate of change. Well, we're talking about these 2 points here at B and C. Ms. Pariar, tell me what that slope is. Positive. Greater than 0 or positive. All right, everybody, figure this out. Talk to your neighbors about it. Limit as x approaches b of f of x minus f of b all over x minus b. There's one more thing that we have to do before you guys leave. So please just bear with me while we do this. If we take 2 points, one that is approaching f of b and f of b. F of b is right here. We're taking another point and we're saying get it infinitely close to f of b. It's the formula for the slope of a tangent. Mr. Abbott, what do you think? Positive, negative, or 0 for that location? Well, I take a point right here at f of b. I take another point and I get it infinitely close and I connect and extend. What does that look like? 0, right? What about this? F prime of c. This is the easiest one to understand. What's that, Mr. Wright? Look at C. C is right here. This notation says what is the value of the slope of the tangent to the function at C. Here is C. sketch a tangent line. What do we got? Positive. Okay, positive, greater than 0. Two things. Slopes of tangents only exist when this limit exists. Slopes of tangents do not exist if slopes of values won't approach the same value. So at sharp points or cusps, we do not have a derivative that exists. This is what we call a cusp. There is no slope of a tangent at a sharp point because the slopes to the left are not approaching the same value as the slopes from the right. The slopes from the left are all positive. The slopes from the right are all negative. So we would say at this location C, the derivative does not exist. Same with a sharp point. Derivatives don't exist when we have discontinuities. Function must be continuous. To be differentiable. If you are told that a function is differentiable, that implies continuity. So a differentiable function f has these characteristics. Just by it saying, the question saying this function is differentiable, you know the function is continuous everywhere. And you know that the function doesn't have any sharp points or cusps. Last thing that we didn't get to, but you will have to kind of watch the video here to understand, I'm going to do it right after you guys leave, is how to sketch a tangent slope function. It will be on your quiz that I'm about to give you right now. Please come in. So we have a function f of x. What we will do is sketch the derivative function f prime of x. It's very simple. All we need to do is look at locations, sketch tangents, and understand their slope values. This tangent looks to be negative. It's a negative slope. This is a 0 slope. Positive slope, 0 slope, negative slope. So we go from a negative to a 0, a positive to a 0 to a negative. We're going to sketch those values, not anything else besides values. Here we have a negative value, a 0 value, a positive value, another 0 value, a negative value. Okay, so negative values, plot it in the negative y-axis. 0 value here, positive value here, 0 value here, negative value here. We've just created a tangent slope function f prime of x. For the next one, I want to sketch f prime, which is the tangent slopes, for all points on this original function f. Now, we're just going to take a few, but by connecting and extending, what we will find is all of the tangent slope values everywhere. We can see, like here, between 0 and 1, we have a positive tangent slope value. Well, between 0 and 1, I have a positive tangent slope that I can find. So we're just taking a couple examples, connecting them, and we will find that connecting them will produce another function that will tell us tangent slope values. Okay, so we have here this tangent, there's one, and there's one. We have a very positive value, a less positive, a 0 value, a less negative, and a more negative. And I can plot that here on this graph. So for -2, I want to plot a positive tangent slope value. Then for -1, a less positive. Then 0. Then a negative, and then a more negative, creating this F prime graph. And I'll finish off and do one more. For this one, all of the tangent slopes at all the locations are the same. They're all negative, and they're equal values. So this is what F prime would look like if this is F. You will see on your quiz, as well as on your test, you will be given the graph of F, and you will be asked to match the derivative function. All I would like to do is just maybe pick out some points that are very interesting. This is a location of a 0 slope. This is also a location of a 0 slope. So I should see 2 zeros. I see a 0 here, 0 here, 0 here, 0 here. So it's definitely not A. It might be B or C. Well, I know we have positive tangent slopes to negative tangent slopes to positive. So I should be looking for positive values to negative values to positive values. B would be our answer. Okay? Please rewatch this if you need help or do not understand. I'm here before and after school. Make sure you do your quiz. Have you been in?